Hello calculus students, here we are with section 6.3, Riemann sums and definite integrals. Now notice I skipped section 6.2 where it 6.2 is a discussion of how you can use limits to find the area under the curve. And the Riemann sum is a continuation of that. But basically I'm not going to hold you responsible for the stuff in Riemann sums or evaluate a definite integral using limits. We're going to focus on just the application of definite integrals and how to find them. But I want you to get an idea of where the integrals are coming from. So just listen to this first part and then I'll show you where you should start taking notes. And basically a Riemann sum is a way of breaking up an area under a curve into a bunch of little rectangles. And then you do this process, you sum up all the little rectangles, where delta x1 is the width of any given little rectangle and f of c1 is the height of it. And basically that's the area formula for a rectangle. Rectangle area of a rectangle equals height times width, right? And what we're doing here with the limit as n goes to infinity is we keep on breaking up this whole thing into smaller and smaller rectangles. So let's say this was n equals 5. Let's say I did half as many or twice as many rectangles. I can get a more precise estimate of the area. And so we look at this limit as n goes to infinity. And the idea of a Riemann sum is as long as the smallest delta is approaching 0, all the rest of them will approach 0 as well, and you've got a process that will give you the area under the curve. There's a little formula for the area of the interval in this case. And basically you can find these limits with a lot of tricky formulas involving summations and so forth. And we come up with this area being 2/3 underneath the curve here like this, and above the curve it's 1/3. Now, here's what a definite integral is. It's this limit as the sum of all these values as n goes to from 1 to n, as these partitions get closer and closer to 0. Okay? And to get those partitions to be closer and closer to 0, you let n go to infinity. So basically you have an infinite number of little rectangles adding up that will give you the precise area under the curve. And then here's an example of, you won't have to do this using the limit theories to find the area under the curve. We're going to jump right into something else. Here's that idea again, and notice how this area ends up being negative because the area underneath the axis is considered negative, and this is positive. So the sum of all these ends up being something negative. That's what they get in this one, -3. So we're going to see that's a possibility for an integral. Now, here's where I want you to start taking notes. Start taking notes. This is the skill I expect you to be able to understand, and the notation. So our definite integral as opposed to indefinite integral. So let's first just back up for a second and say that indefinite integral is what we did in the first section. An indefinite integral was something like this symbol of x squared dx. And we came up with x cubed over 3 plus that constant of integration. There's that indefiniteness of it. It's a whole family of functions. Now we're going to see that when we do this integral from a to b of f of x dx, this is the definite integral, and it gives the area of a region. Now, there's a few things you have to note in the notation here. See this a down here? That's a limit of integration, and that's x equals a, and this is x equals b. And that corresponds to these lines, x equals a and x equals b. That's two things that bound the area. You also have the function itself, y equals f of x is the upper bound, and then the x-axis forms the other bound. So those are the two things, the vertical lines on either side of the area, x equals a and x equals b, the function itself, and the x-axis. And that's what I mentioned down here by the 4 things that bound that area. Now, here's an example. We have the function 4x minus x squared that has roots at 0 and 4. And so we can find the area under the curve with the area from 0 to 4 of 4x minus x squared dx. And at this point, I'm going to have you practice doing this on your calculator. And so let me show you where it is on the calculator. So you have that skill ready. I also want you to know how to do it by hand as well. But we're going to emphasize both skills here as we're going through this. And And then maybe you'll find out what's the mystery behind finding this area, because we can't break this one up into a bunch of little rectangles and triangles and so forth, or circles. So on the TI-89, you can do it like this. On the TI-89, the integral symbol is above the 7 key. Above the 7, you're going to see this funky little squiggly line like that. That's your integral symbol. We also use it for antiderivative. The integral of, left parentheses, 4x minus x raised to the 2, comma, now you're taking the integral with respect to x, comma, and then you put in the limits of integration from 0 to 4. Okay? And when you do that, you get 32 thirds. 32 thirds. See, we got this 4 by 4 big square, which would have been 16, and 32 thirds is a little more than 10. That looks about right. Now, we'll come back to this again in future chapters. In 6.4, we'll actually do the fundamental theorem of calculus and see why that works. But for right now, we're going to stick to doing the integrals of some common geometric figures. So in example 3 here, we're going to find the integrals of each of these by looking at this as just a rectangle. Our curve in this case is just the constant function 4, and we're going from x equals 1 to x equals 3, so it's just a rectangle that's 3 by 4. So this integral equals 12, and you can check it on your calculator if you like. Let's try another one, b. Now we've got the line x plus 2, going from 0 to 3. Now, you got a couple choices here. You can use a trapezoid rule, or you can break it up into a triangle and a rectangle. A triangle plus a rectangle. And the rectangle is 1/2 base, which is 3 times the height, which is 3. And the rectangle is 3 by 2. So we get 4.5 plus 6, 10.5. So this integral is 10.5. Integral from -2 to 2 of square root of 4 minus x squared dx. This is actually something we're going to have a very hard time doing by hand because it's this complicated integrand. But we can see it's a circle, because if y equals square root of 4 minus x squared, then y squared equals 4 minus x squared. You get x squared plus y squared equals 4. This is a circle with a center at 0, 0, and a radius equal to 2. So, but it's only a semicircle, because if you solve it in this direction, you just say plus or minus, but we only have the top half. So it's a semicircle. So we get our formula for the area of a circle, pi r squared. And we take half it because it's a semi. So 1/2 pi times the radius, which is 2 squared, and we get 2 pi. So this integral equals 2 pi. And you can verify that in your calculator. It should give you exactly 2 pi on the 89s. Now there's some special integral rules. That is, if we do the integral from a to a, if the limits of integration here are the same, then basically you've squeezed your area into something like this. Here's your function. If you're going from a to a, you got no area. So that's why that's equal to 0. And if you go from a to b and find an area under the curve, a to b, and that's your integral. If you go from b to a, it's like you're doing the dx's in reverse, and those end up being negative, and it gives you a negative area. So that's why it's the opposite. If you switch the limits of integration, you end up with exactly the opposite answer. So in this example, somebody went from 2 to 2, so we didn't really have to go through a lot of work here. If these are the same, you get 0. If the limits of integration are the same, you get 0. And here someone has gone from 3 to 0 of x plus 2 dx. Well, you can think of it as the opposite of the integral from 0 to 3. So notice what's switching there. The limits of integration flip. And that's why you get exactly the opposite answer. Now there's also the additive interval property. That is, you can add up integrals, definite integrals, as long as you've got to have some things the same here. Notice what's the same in these two. Let's look carefully here. We've got f of x is the same dx and f of x dx. We're looking at the same function. And further, you've got to make sure that they're connected by a limit of integration that ends one and starts the other one. So look for that carefully before you go ahead and combine or split up some things like that. Now, using the additive interval property, we're going to apply that here when we've got a funky function like this, which is the absolute value of x. Absolute value of x does this, and if we want to go from -1 to 1, we want to split it up into the integral from -1 to 0 of the absolute value of x dx, plus the integral from 0 to 1 of the absolute value of x dx. And as a result, when x is less than 0, the absolute value of x is basically equal to x. So you get the integral from -1 to 0 of x dx plus the integral from 0 to 1 of x dx. I'm sorry, this is when x is less than 0, the absolute value of x equals the opposite of x. So you get the opposite of x there. When x is greater than 0, if x is greater than 0, then the absolute value of x equals x. Okay? Now, either way, I do this because you're going to want to split up like this when you're going to have to do it by hand. But right now you can see over here that you've got two triangles. The left triangle added to the right triangle. And so this is 1 and 1, and this is 1 and 1. So it's 1/2 base times height plus 1/2 base times height. And we get a half plus a half equals 1. So this ends up being 1, and you can check that in your 89. Now, properties of definite integrals. Here's that constant multiplier rule again. Notice how the constant k here can just come on out, just like it did with the derivatives. Isn't that handy? And also the idea that you can distribute this derivative idea over addition and subtraction. So the integral, definite integral of a sum or difference equals the sum or difference of the definite integrals. Now, let's evaluate some definite integrals here using each of these following values. That is, we're going to apply this property of splitting things up. So I'm going to split this original expression, the integral from 1 to 3 of -x squared plus 4x minus 3 dx, into integral from 1 to 3 of -x squared dx, plus the integral from 1 to 3 of 4x dx, minus the integral from 1 to 3 of 3 dx. So that's this concept that you can distribute the integral, the antiderivative, over addition and subtraction. Now, we can also take out these constant multipliers, these constants. This negative inside the integral can come outside, so it's the opposite of the integral from 1 to 3 of x squared dx, plus 4 times the integral from 1 to 3 of x dx, minus 3 times the integral from 1 to 3 of dx. And now we can come back up to here and say, hey, they told us what the integral from 1 to 3 of x squared dx is. That's 26 thirds. So all that's 26 thirds. And so we have the opposite of 26 thirds plus 4 times, and now we can look over here and see that we've got the integral from 1 to 3 of x dx is 4. So that's 4. Minus 3 times, and finally let's look at here, right here we've got the integral from 1 to 3 of dx equals 2. So that's all 2. And so now, let's get another page in there and back up. I thought I put another page in, sorry. Here, put another page in, there we go. Now we can start adding these up. We get minus 26 thirds plus 16 minus 6, minus 26 thirds plus 10, minus 26 thirds plus 30 thirds equals 4 thirds. And you can actually check this on your calculator. Let's do a TI-89 check. Integral of negative x raised to the 2 plus 4x minus 3 comma x going from 1 to 3, and let's see what it says. And sure enough, the calculator agrees with me.